Hi, cool. All right. Hey, everybody. Welcome to June's DPRG monthly meeting. Very short list just to run through. We have Moon Day coming up at the Frontiers of Flight Museum, July 18th. If you're interested in volunteering, member or not, come see me. We'll get your name on the list. We have, I think, 5 or 6 volunteers right now, which is great, but more is always welcome. So yeah, let me know. July 18th for that. Other than that, the next meeting, which is on July 25th, we don't have a speaker, so we'll have a show and tell. So bring your robots. Let's see what you got, see what you're working on. If you have any surplus stuff that you don't want anymore, we have a swap meet. So bring your junk, and then we'll, yeah, it'll be a good time. No, this is for the Robot DPRG monthly meeting. You're welcome to join us. Also, this Wednesday, we're going to restart the workshop Wednesday, where we're going to meet together here in animatronics and work on Roby right now, try and get him ready for Moon Day. We have a new neck mechanism, courtesy of Mark. We can show it if you want. Yep. Give a quick presentation to those online. So previously, yeah, let's put it down here on your desk. Previously, the neck mechanism for Roby consisted of a long metal shaft that went from the neck all the way down to literally the gut of Roby, with a motor and a very interesting way of controlling it. So Mark has redesigned it to be all self-contained. So this will sit on the neck itself with a stepper motor internally, and then of course this is going to sit on top with another stepper motor. Yeah, so it's going to be an interesting neck. It's going to be a good neck.
How does it know what position it's at?
Well, we'll figure that out. No, there's some of the stepper drivers or stepper motors that Mark put in have. Oh, Mark, what did you say it was called?
So the stepper motors, the drivers that are wanting to use are a trimatic driver, and they have a homeless homing sensor in them, so they can actually detect the stop in motion. So when you start it up, you'll be able to essentially run it to. The idea is that you would run it to the stop, you would detect the stop, run it back the other way, detect the stop, and then you could center off of that. Yeah. So basically, it has a sensorless homing.
So we're gonna try that, see if we can get that to work. If so, we'll use that. Otherwise, we have some
it's
fallback.
It's the same drivers that they use in a lot of the modern 3D printers, and so that's what they use for actually detecting the carriage position when they. That's why they slam them into the wall, is to basically detect the homing point.
Yeah.
What does the endpoint detection look like? Like, is it a fourth wire in the interface?
Yeah, it's basically there's a additional wire that basically signals a fault when the motor stalls,
okay.
And so you can use it for stall detection. You can use or for homing.
So you feed a fourth wire in or a second wire into the Arduino or whatever's controlling it.
Yeah.
Oh, cool.
That is cool. So we'll give that a go.
Yeah.
So yeah, that'll be Wednesday the 1st, this Wednesday, 6 o'clock. If you're available, come on down. Again, you don't have to be a member of the Makerspace or DPRG, but if you come here, let me know. I'll open up the door and we'll work in the animatronics workshop.
You said you do not have to be a...
No. We just appreciate the help. I mean, it helps to be a member. But yeah, certainly don't need to be. But that's it. That's all the notes I had. You thought of anything else we could add? No? All right, then without further ado, I'll hand this back to Paul, and then we'll get Mark up and running. Thanks.
Myself and Mark, you're up.
So I get to try not to embarrass myself. So today I'm going to essentially introduce a project that I've been working on for a little while as kind of an alternative methodology for creating more complex hardware systems, such as robots. So today we're kind of going to focus on the robot access and also the first step, which is actually creating hardware modules for controlling your robots. Just to give a quick little background on myself for those who don't know me, I'm Mark Dombrowski. Nice to meet everyone, including some of the new people that we see here. My background is by training, I'm a computer scientist. I got my degree from New Mexico Tech in Socorro, New Mexico, and then spent the first half of my career doing large-scale weapons and building simulations for the U.S. Department of Defense, for the Navy and the Air Force. And the second half of my career was spent in the electronics industry doing reliability testing for semiconductor systems. So that's kind of my background. And I kind of went from doing mostly software development to more of a jack of all trades, doing electronics, project management, mechanical engineering. So I've got a wide background in things. I've always been a tinkerer. So, and this is kind of a culmination of my desire to try and get projects done, in which I always get stumped, usually when it comes around to the electronics. And so I have a tendency to stall out. So I wanted to try and solve that problem. So.
Mark, before we carry on, can you join the Google meeting and so that you're and share your desktop, or at least share the slide set? So
I'm not set up online.
You can join the Wi-Fi there, because I think that will get much better recording, and it'll be much more visible, because the slides really are not readable for people online.
All right.
Sorry, I should have thought of this before we started. So join Wi-Fi DMS member. Okay, I'm just admitting you.
Okay.
Hang on, where are we? Where are we? Oh yeah. Okay, now you're in.
Okay.
So you should be able to share your. So sharing is that screen with an up arrow.
Let's do that.
Perfect. Thank you.
Now, if I can get back to
Good. Your slides are being shared, and
but
and then I've got the video and audio come off my laptop, so the recording will work.
all right. So we'll go back to the beginning.
Okay. All right. Sorry for interrupting. Thank you.
No problem. So first, let's kind of define the problem. Even though robots are easier to build today than they ever have been, robots are still considered hard. And one of the main reasons why is because they require a lot of different disciplines in order to actually construct a successful robot. You've got to deal with electronics, firmware, software, mechanical design. And so trying to gather all of those skills in one mindset, especially when you're first trying to start out, can be rather daunting. And so the idea is that we want to try and make that. So most people try to learn it on their own. So they want to design a robot, so they sit down and they start tinkering with it. And it's easy to get lost and confused when you move on to a discipline that you're not used to. Most of us in here are older and have had lots of decades to gain all of those skills, but especially for people starting out from new, it can be a little bit daunting for where to get started. The other thing is, since we tend to do this hobby typically on our own, we tend to come up with a lot of our own solutions. So every time we design something, we have a tendency to sit down in our own heads and we design out a solution, and that works fine. But as everything grows, since we're kind of growing everything organically, we get things tangled up. You get your mess of wires between trying to get all of your sensors and modules hooked up. Everything gets kind of jumbled, and when you try to add things or expand things, it becomes more difficult to do. So just in general, there's all kinds of headaches involved in building up a robot, and especially when it comes to trying to wire in all the electronics and get everything working for various different systems on the robot, like getting the drive system going, getting the sensors going for maybe you're doing a can detection sensor or you're doing a wall detection sensor. So trying to basically manage all of those and kind of juggle them around. So a typical approach that we'll often do is we all start with these little modules that we can all buy off of Amazon and eBay and AliExpress. And so these little hardware modules have actually made our lives a lot easier, but they're also rather difficult to deal with sometimes. Oftentimes you've got to be able to find the drivers and all of that. So typically we'll want to do something like a motor control. So we'll find a motor control driver online, and then we'll pick a microcontroller to drive it, that you need to actually drive the chip. Then you need to find the drivers that'll work properly with your microcontroller and everything else. Then you'll code up a simple test script to basically try and get things working. You'll start adding in a bunch of debug prints, and you'll finally get everything working and tuned the way you want it. And then you'll go, okay, now I need to communicate with this from the outside world. So now you've got to stop and figure out how you're going to wire up a protocol to talk to it, and how you're going to basically drive everything from your robot. And so those are kind of some of the problems and difficulties that we run into, that and tripping over chairs. So what we want to try and do is design a system to try and make some of that stuff a little bit easier, and to try and structure some of that stuff a little bit better. So there are systems out there like ROS that does this to a large extent. So ROS is basically a kind of an event-based system that basically fires off events and talks. It has a couple flaws. It has a large learning curve on its own. It's based on Linux, so you basically have to drive it from Linux. And there's other frameworks out there too, but so I wanted something a little bit different. I wanted to create something a little bit simpler to kind of help with the design. I wanted it to be scalable, and I wanted it to be able to be used by younger people. So for example, I've been using it to help train my nephew electronics. So what do we want out of a solution? So we want to create a modular system that's basically easy to use for developing hardware. We want the modules to be simple to create, share, reuse, and also replace. So that if we are building as our robots get more complex, we want to basically have modules that we can basically deal with. We want the focus to be more on the overall system design rather than getting bogged down in the details of the modules themselves. So the idea is to try and, when we're designing our overall robot, that we actually look at it from kind of a top higher level view, so that we don't get lost in the weeds when we're trying to fight with the motor controllers and the sensors and all of that. So we want the system to play well with development teams and individual projects. So one of the goals that I have for this is, as our projects get larger, we as a club, for example, have talked about doing team projects such as Ravi or other robotics. So I wanted a system that basically scale and allow the steps to be kind of broken apart across teams, so that people can kind of focus on their individual skills, but still be able to come together and build something out of it, to try and encourage being able to do team builds and things of that nature. And so that was one of my goals for the system as well. And then obviously to make it cross-platform, so that you're not limited to Linux, so that you can run Windows or Mac or whatever you wanted to run. And so with that, this is my humble attempt at trying to make a system that hopefully tries to make the electronics and kind of design of robots a little bit easier. And in particular, this is kind of the first step of the system. So the main thing Modlinker is trying to do, as again mentioned, is it's meant to be a modular-based approach to hardware design. So rather than, so you design the system by breaking it up into smaller chunks. The old adage of how do you eat an elephant one bite at a time. And so the current beta is basically based on Python, MicroPython, and the Raspberry Pi microcontroller family. So I chose Python and MicroPython because it's extremely accessible. There's lots of tutorials for it online. All of the AI tools are actually highly optimized for Python these days, because Python's been one of the more common languages for the past several decades. Python is usually a teaching language. It's used in schools, so that's a good basis for it. And I know that a lot of us here use it as well. So the reason for picking the Raspberry Pi microcontrollers, one, I like the Picos. They're a nice microcontroller. They're cheap, and they have a lot of nice functionality to them, including the dual core, the PIO, all the handling for the I/O for when you're trying to hook up to various different modules. They have a good support community online and one of the best documentation for a microcontroller out there. And so that's kind of my starting point for this. So the main parts of the system are the main goal. The main core to it, much like ROS, is essentially a custom protocol that basically is used for communicating between between microcontrollers. As you'll see as we progress, the system is designed to actually use multiple microcontrollers rather than trying to cram everything into a single microcontroller. And so the core of the system is essentially a communication protocol that basically talks between the microcontrollers. There's also a toolchain, and the toolchain is used for essentially managing that protocol and making it easier to work with. And so as I show you, when we get to the demo, we'll demo how that works. And then there's soon to be some custom dev boards to make designing your projects a little bit easier. And I'll show these in more detail later on as well. Right now, I've got a couple different prototypes of the dev boards, but I'm trying to finalize a few bugs in them to get them going. I was hoping to have that done by now, but I don't. So one of the things that Modlinker does is I kind of redefine the definition of what is a module. So we commonly think of in the electronics, as we're used to it, a module is essentially, like I showed before, something like a motor driver or a angle sensor or something like that. Modlinker basically treats the module as essentially a microcontroller as well as those components that it's driving. So it's we kind of refocus the module on having the microcontroller along with the drivers to drive it. They're designed to present basically a more approachable level, a more abstract level to the hardware that you're driving. And so, for example, with a motor driver, rather than worrying about, say, a stepper motor, worrying about doing the individual steps, you might have it set up to where you want to control the speed or you want to control the RPM. So basically, the idea is to try and encapsulate that interface to be a kind of a higher level interface to the module, to make the module easier to integrate in to different designs and to share. Ideally, the modules would perform one main function. So for example, in a robot, you might have a module that controls your drive system for moving you forward and backwards and turning. Another module to maybe do can detection, for example, or a module to do wall detection, or basically by taking each module and breaking it up into smaller steps, it makes them a little bit easier to construct and a little bit easier to share and connect. So each some of the key features for a module is that each module basically knows its interface. So as you'll see here, that's actually the key for making the system work. And what I mean by knows its interface is that you can actually query the module and actually get its interface from the module itself. And so you can use that to basically help you in constructing tools and drivers and debugging it. Modules are chainable, so simply basically connecting, you can basically connect modules together simply with a 4-wire cable, and that basically chains them together. You can also basically daisy chain power and all of that. And that's something that, so basically the modules basically chain from one to another. So the communication protocol actually is a serial chain that bounces from module to module. So,
one question, when you said modules know their interface, do you mean that they know the device, sensor or motor that they're supposed to be looking after? Is that what you mean by the interface to that thing?
Yeah, in a way, when we get to the demo, it'll become a little bit more clear.
Thank you.
So, okay. So speaking of a demo, let's go ahead and give a quick one here.
Do you want to unshare and then the camera will go full screen?
If I shut that down, and it should be full screen on. Do you see full screen?
No, you want to go to the Google Meet window and click the sharing button and turn that off. Oh yeah, sorry. Yeah, it's off.
Okay.
Sorry. Yeah.
So,
Yeah, I could share my screen and then let's see if that works.
You're going to be showing code?
All right, now I'm going to show.
Oh, no, that didn't work. Yeah,
Do you have?
he would
the-
have to do. He would have to display that.
Do you see this window up there?
Yeah.
Is it showing up on the Meet as well?
Hang on.
Is it showing up on Meet as well?
No. No, you'd have to reshare your window.
I thought I was sharing that second screen. Oh, did you stop my sharing?
No, I didn't, but you may have. If you reshare it with the button with the picture of the screen and the arrow. Yeah. Yep.
How about now?
Okay, yeah. Now it's showing up on the recording.
I don't know how to minimize that window.
Yeah, that's always a struggle. I just like grab the top of it and move it right down into the bottom corner of the off screen kind of, and that's about the best I can usually do.
So this here is one of the beta tools for actually using this protocol. So right now I'm plugged into my example motor driver, which I've demoed previously. So I'm just plugged into the into the Pico with a serial cable, and so I can connect to the. So I'm going to connect to the module with this discovery tool, and it's going to query the interface, and then it's going to automatically populate out the interface for that module. So you can see that we've got we can get the current wheel position, which is a reading off of the angle sensor that's in the wheel. We have the names of the module, the manufacturer version. We can basically set an RPM, so we can say, or in this case, we're just turning it on, so we can set the motor power at 50%. And so it'll spin at 50%. So when I say that a module knows its interface, it basically can send its interface off to, in this case, it's this discovery program. And what it does is it automatically builds a graphical user interface based off of the defined interface inside the module and gives you a way of essentially driving it and testing it. So this is all automatically generated. Let me turn the motor off here. And so I also happen to have this motor. You can also set the RPM of the motor, and it will essentially use the angle sensor to maintain the RPM. So basically what you have here is over here on the side is essentially all the commands that are going across the interface to it at the moment, because I'm currently have it in a debug mode. And so it's basically showing what's getting sent across on the protocol. So you'll see as I make a call, like for example, turn the motor off, you'll see that the command is sent across. So the idea is that once you have your module created, you no longer need to basically worry about a driver or anything like that, because you can basically generate the driver dynamically. And so you can use that for debugging in this case, or you could actually use it for driving to learn about the module that you're working with. And so it's a system for basically creating a top-level interface and then being able to command that via PC or or from a larger larger controller. So I'm going to go ahead and disconnect from this one real quick. And I'm going to just plug into the right one. So this is just a Pico that's running a simple blink module that I coded up, and we're going to actually create this one here in just a minute. And so I can take that same discovery tool, and now if I connect to this module, if I select it, actually get the port selected and work my mouse correctly. So now I'm connected to this blink module, so I can basically change the blink rate. So I can change it from half a second to a quarter of a second. And so it's just so basically I have an interface for driving this. It's automatically generated off of the module itself. And what I'll do here is I will wire in a second one here by chaining the power, and they're just chained by essentially a serial connection. And now when we connect up to our modules, it's going to basically give us both modules. So now we have each module on its own tab. So we can go on module 1. And we'll have it blink at 100. And we can go to the next module in the chain and have it blink at 750, for example. And so just by basically chaining these, so you can see how if you had a robot that had a motor driver module in it, a wall sensor module in it, or something like that, you basically have one connection in, and you can chain and command all the modules down the chain.
When you chain it, the overall speed of the system should drop, going down.
By
For example, if you have a module for camera, and you chain more modules, it will drop the speed.
it can drop the speed, yes. In general, the chaining is relatively quick. The idea behind this isn't necessarily a high-speed interface. It's meant for more high-level control. And for a high-speed interface, you can basically run multiple chains. So if you had a camera, you could actually run a dedicated chain for your camera module, for example, so that your PC could basically keep up with it.
Another question.
Mm-hmm.
The bar would have a kind of old procedures. So is it when you plug in, for example, I got a module that I'm not clear about.
Mm-hmm.
I do see interface and deduct what is wrong.
Yep.
Obviously, if I got it, I know. But as well, will provide me some information about high level about what functions they do and how to code it.
Yeah. So this tool here is kind of a discovery tool. So what it does is it actually presents you with all of the functions, and you can actually call them, fill in their parameters, and get the results back. So, for example, on that blink on I'm actually setting the parameter in here that's being sent across. The other thing that this program does, although I have it disabled at the moment because I'm debugging it, is it will actually create a driver for you. And what it'll actually do is it will use the same information. It's actually used in the background here, but what it'll actually do is create a Python class for you that basically is the driver for that module. It can also create a class on the fly for the entire chain. So you can actually create a class that basically encapsulates an entire chain of modules. And so it basically can, because of the fact that all these modules carry their interfaces with, and that you can query that interface, you can construct tools that will automatically build the drivers for them, or automatically build debugging windows such as this for being able to debug and drive it and discover how the module works.
So, just curious, so the module itself basically, see if I'm getting this right, as an interface class. And you just query the class, and then it just spits out all of its, I guess it would be their public constants.
Right.
And so, okay.
Okay. So this kind of shows how it works. And now, of course, the big question is, okay, so how do we create one of these things?
But you're not going to be used, well, if you,
So the way you would use this is, right now you have this interface is basically displayed for you.
I'm not going to be using, well, this basically says you have to have a Raspberry Pi on your computer or PC somewhere doing something, no matter what it is. But there's always some computer running an operating system.
Right.
So a lot of robots don't really have anything near as complex as Linux on them.
No.
They might have where it's very different. Arduino loop function. Yeah, it could be that. That'd probably be your simplest. But I was thinking more as tasks that it you know, be round robins through a bunch of real-time OS kind of thing.
Yeah.
But it's not anywhere near Linux, you know what I mean? Linux is got a lot of overhead compared to an Arduino loop. So the question I have is how this one is always going to have high-level OS somewhere in the system.
Or
otherwise, I can't do this straight M4 ARM.
actually you can. And the basically there's no need to actually drive this from a higher level PC. You could drive it from a microcontroller. Because the protocol, the idea would be to basically build out a driver. So right now this is kind of centered around Python and the microcontroller, and using a host computer, simply for ease of development and for basically me debugging it and getting the system up and running. But the base protocol behind it is just a character stream. And so anything you have that can essentially stream characters to a serial port can drive it. And
I'm just trying to understand what's going on. So let's say I am using microprocessor. I guess it wouldn't matter even on your PC. Each module has an interface. So obviously, top dog, whatever it is,
has to know, be able to recognize that if I have this, or probably a module
Mm-hmm.
that tells me like, okay, this is a motor driver.
Yep.
You know, it's got somewhere you have to have a list of all the modules so that it can interpret what you're sending.
Right.
Because just saying, okay, give me, you know, tell me, you know, the public variables. If you know, it has to know more than that.
Right.
Yeah, it has to know what. Yeah, I'm looking at a motor control.
Mm-hmm.
So that's.
Yeah.
Where does it do that? Does it do it by a module name, or does it do it?
So there's a couple of ways to do it. The modules are dynamically addressed, so as you do it, everybody gets a unique address. Unlike using a protocol that requires assigned addresses or whatnot, these are dynamically assigned. You can yes.
And so is it this display of stuff?
So the address is basically given to it next to there. You can also identify modules by their name, manufacturer, version number. You can get their descriptions. Those are all basically standard methods of the module itself. You can basically assign names to modules so that you can basically reference them by assigned name, by an alias name. And so the idea there is that, let's say we were doing like Robbie. And so let's say we created a module for his hand, and a module for his arm, a module for his neck. You could basically do the series, and you could actually name those modules, and then you could basically call out those devices when you're connecting them up. Right. Yeah, the main program would essentially consist of would basically consist of a bunch of classes for controlling each one. You'd basically connect your class to the given chain manager, which in this case would be a serial port. So you'd basically give the command chain its serial port, and then you would basically have all the classes would basically automatically connect to the chain and be able to talk to the chain.
This one I'm sure I understand. So the interface is exposed by the module.
Mm-hmm.
That is based on whatever it's called. The main program knows that if something's called this, that this is its interface.
Yep.
Okay, so it's not a case of this guy dynamically picking up the interface from what's presented by the model. Otherwise, it doesn't say, oh, this thing's got a speed. Never mind. I'm just
No problem. I understand. So,
sorry, one question.
okay.
Please forgive my ignorance.
Oh, no problem.
I'm just tagging along with my son. I'm not even in all this robotic stuff.
I'm okay. This is informal.
So is this program accessible to people or is it by
It-
subscription?
I haven't quite decided on the model for it yet, but yes, it's going to be available to everyone. Yes. This is something that I created and wrote. It kind of stems from when I was working on prober systems and having to deal with a whole bunch of different vendors and whatnot. We were developing a complex prober system that involved had a heating and cooling system in it. It had 120 SMUs. Actually, it had more than that, but I'll say 120. SMU is a source measurement unit, so it's for basically measuring applying a voltage and measuring the result back. They use it for instrument testing. And so we had to coordinate all of those and get them to all talk with each other. And this was kind of a backbone system for essentially putting those type of systems together. This is kind of watering it down a little bit and trying to make it a little bit more approachable and putting it into a robotics context. But in actuality, you could use it to design just about any system. The goal is to essentially manage a protocol so that you can basically take various different pieces. You can develop those pieces independently because their interfaces are well defined. And then you can plug them all together back at the end and actually be able to drive everything without having to worry about all the mismatched interfaces and all of that. So as I was saying, the next step is to probably show, okay, this all sounds well and good, but what's the process of actually creating one of these? And how do we go about doing that?
But before you go there, to follow on from Mo's question, is it, about the accessibility of this. Is the code up on GitHub or?
Not yet, but that's
okay.
what I'm planning on doing.
That's
Yes.
where you'll put it. Okay,
Yeah.
cool. Thank you.
Right now, as was mentioned in the product brief, I'm kind of looking for beta testers at the moment to try and help me debug this and also come up with a few modules. And so that's going to be one of my requests at the end, is to ask for people who might be interested to be guinea pigs is whether they would like to try out the system, because I kind of want to, before I release it to the public, I kind of want to get a little bit more feedback on it. So, but eventually it will be released, the Python version at the very least. And I'll kind of go into that a little bit later on as we go.
Thank you.
All right, so the first step to actually designing a module is to basically design the interface. So let me pull up an example interface definition. And I'm going to pull up the simple one for the Blink module, and then we'll I'll kind of explain it. So these modules are defined by essentially defining an interface.
Much better.
Are designed by essentially defining an interface for the module. So you're basically creating a list of all the things that define it. So you give so you start off by basically giving it a main module and a description for what the module is. You have a couple of required assignments for the name, the manufacturer, and the version, which is how you can basically identify some of it's a methodology for doing the margin. And then you basically start listing out the commands you want your module to have. The commands are relatively simple if you're familiar with Python. They're using kind of a Python syntax and the Python type notation. So you have, in this case, you have a difference between commands and messages. So in the protocol, a command is something that returns a value. So a command is a two-way communication contract with the module. So you send off you initiate the command, and the module will give you back a response. A message is a broadcast, is essentially a one-way message that basically only goes down. You can send it to the module, but you won't get a response. So the idea behind the message is, if it's not critical that you get the response, you cut the overhead of having to deal with the response by having the message. The protocol also supports events. Events are a way for the modules themselves to essentially message back to the host. So an event will basically travel back up the chain to the host. It will also go the opposite direction down to your siblings so that your siblings can actually handle the event. You can also have event handlers. Event handlers essentially will basically give you the infrastructure for handling the event as you're doing it. But for now, I'm just going to focus on the commands and messages just for the simple demo of how we actually go about building this. So you basically define this module definition file. So you list out essentially what functions you want for your interface. And so the next step is that we need to essentially we're going to create a project for the Pico that basically gives us a framework for this interface. So we can do that. And I'm just going to, let's create a new folder here.
More is the link module have its own processor?
Yeah. In this case, this is just a simple example.
No, but I'm saying that it's really communication microprocessor to microprocessor.
Right.
That's why you get away with things like delay instead of taking
Mm-hmm.
I'm just trying to. Okay.
Well, as you'll see when you actually design when you're actually coding up the module itself, you can still do all of the same things that you typically do in your microcontroller code. So.
Yeah, because it's got its own micro. So you
Right.
essentially dedicated a microprocessor, which is cheap, to blink an LED.
Right. In this case, this is blinking an LED, but in reality, it would be something like a motor driver or something more complex. But just for an example, so let me go ahead and delete this out of this directory.
With 5 servos, would there be like 5 servo modules?
You could do it that way, or you could do it as a module that basically control multiple servos. So you could design it such that you could control multiple servos. So for example, what you might want to do if you're building a robot hexapod to where each leg is 3 servos, you might want to create a module that basically controls the hexapod leg itself. And then you could basically duplicate that module for each leg. And then you would chain them all together, and then you could basically talk to all 6 legs. That would be an example. Or you could do it as the hexapod itself as a module that drives all the legs, but then you're kind of missing out on some of the ease of the abstraction. If you abstracted out the leg, you could create a hexapod that had 4 legs, or a hexapod that had 8 legs, by essentially duplicating your module.
Okay, so somewhere the master controller is going to have a buttload of serial ports.
Just one. Like I said, the modules are chainable.
Well, daisy chained.
Yeah, everything is basically daisy chained together. Most people worry when you say daisy chain that it's going to be very, very slow. There is a slight delay between modules. The delay is the time that it takes to send one character. That's the delay that you get between modules. And the reason being is each module is basically processing its data stream a character at a time. And as it processes a character, it kicks it down the chain and then basically continues the processing a character at a time. That's the way the protocol works in the background. So it's not, it's not meant to be a super high speed protocol. It's meant to be a top level control protocol. For your high level speed stuff, you're still talking to all of your submodules the way you normally do over SPI or I2C, but you're isolating them more onto the microcontroller to kind of isolate them and then drive them at the higher level where you don't necessarily need the speed. You can use to basically run it.
I think the streaming answer.
Mm-hmm. Yeah. So basically they basically daisy chain from serial to serial port. So this was the first prototype board that I did. You could basically just run the 4-pin cable over and chain them, and it's got basically the cable has a serial transmit and receive, and 5 volts and ground, and so that basically just daisy chains down the modules. The newer modules, as I'll go into the design a little later, the newer modules have the same thing. It's an in and out port. The new modules also have a prototyping space. So you can actually, they basically have a hat system that's associated with them. So you automatically get a prototyping space for basically soldering everything together. It also has a daisy chain of a power that will basically take 6 to 30 volts. And it has a built-in 3 amp, 5 volt power regulator that gives you 5 volts. And so it basically tries to simplify the hardware design so that you don't necessarily have to worry about how do you manage your power, how do you manage all of this. It gives you all of that kind of upfront. And so it gives you a good starting point for when you're going to build these.
So it's basically a module, a basic universal module.
Right. And so it's got enough room to put several modules that you want for whatever you're building, or a couple connections. You can have a connection for your 5 servos, for example, and it could be a 5 servo controller. And then the idea is that once you had this module, it would be something that you would be able to easily share and or replace or extend. And so the idea is that your robot would then be essentially made up of a series of these all connected together. And so it's not necessarily meant for small robots or anything like that, but it's meant to help try and make some of this development easier. And so again, what I'm doing here is I'm just going to save this project out to this demo directory here. And so I'm going to create a project. And so what that just did is it just created a Raspberry Pi project for VS Code that basically gives you a framework for dealing with this interface. And now I'm going to show you that. So this is the project that this just created from this interface. So as you'll see, it's got the micro Python code, and then it basically has 3 main code files here that it automatically generated. And so we're going to edit this project. And the heart of this project is essentially this class right here, this ML Blink module. So what it did was it created a class that basically represents your interface. So it gives you a framework for basically creating your module. So in this case, you get a constructor, which basically takes the form of the setup loop in your typical Arduino. So here you would basically put the setup for your module. You have a process idle, which is essentially the same thing as the loop in the Arduino. So that's where you would basically code up your module's loop interface. You then basically get a whole bunch of functions that are defined for you for basically filling in the functionality for your interface. So it generated basically a template code for you to basically have a starting point for building up your module.
See the fixed piece, that's what you have to actually.
That's where you actually put in your code to drive it. But what you get out of this is, so I'm going to go ahead and unplug this module here. Let me disconnect the other one so I'm working with just one. So I'm connected to this module. So if I toggle my project, I don't know why it's not letting me, probably because I'm off the screen or something is confused. Part of it is that I have this window in the way. Come on. So I'm going to go ahead and remove the code that's currently in this mod. So this is just removing the code from the Pico itself. So now I'm going to go ahead and write this project to the Pico. So now I've uploaded the project, and we'll go into a little bit more of this in detail. But I'm going to show you what was actually generated from the code. So what you get to start with. And don't save because that was doing something else. So sometimes it's a little finicky when it disconnects from VS Code. So I'm going to bring up that same discovery program. And I'm now going to connect to the module that we just programmed. And so you'll see that we basically have it already has the code and everything in there for essentially managing the protocol, for managing the interface, for managing all of that. So you don't have to create any of that. All of that basically comes for free by essentially using the system. You'll see right now we can currently get the names of our modules, so we can activate the system functions, no problem. Those were automatically populated. And if we do something like a call our get delay, since we haven't filled that message in, we actually get the error that the command's not implemented. So basically what you have is a full framework that's automatically given to you that manages an interface that's accessible over the serial port. You could chain them together and all of that. And now you have a framework for essentially designing and building your Blink module. So if we go back to code, I'll kind of walk through what some of this kind of does. So this is the main program here, which is your traditional loop in your MicroPython code. This code automatically takes care of the fact that the Pico is a multiprocessor microcontroller. So we actually are running all of the I/O updates. So all of the processing of the protocol is actually being run on one core, and the actual module code itself that actually runs your module is running on the other core. So you automatically get use of the dual core through the system as well. So basically it optimizes so that the protocol handling doesn't interfere with what your module is doing, because it's actually running on the secondary core. And most times, most people don't even bother to use the secondary core or even know it's there. So I utilize it to basically handle all of the processing of the data stream. So it's what's doing all the talking back and forth to the PC and doing all of the it takes care of translating, doing all of the argument parsing and all of that to basically parse your arguments and make sure that they get sent across correctly. And all of that basically is automatically generated for you so that you don't need to worry about that. And it gives you a nice, by using, like, for example, that discovery tool, it gives you a nice debugging tool for when you're going to actually drive it. So unlike, so if we were looking at that blink module, I can go ahead and load up what that actual completed blink module looks like. And here's an example of what this completed blink module looks like. So you'll see here in the init, we init essentially pins similar to what we normally do. I also have a couple of helper classes that are in there. One of them is this ML ticker, and I'll explain it here in just a moment. The process idle loop is what actually runs the blinking here. So what we do is we're setting the rate and the ticker. And so what the ticker does is as you go through the loop, it automatically checks to see if it's time to tick or not. And if it ticks, then you actually run the toggle for the blink. So it's just a simple way of doing a time management. And so you can actually set up several of them and have them all tick at different rates. And so your main loop would basically just check to see if it's time to do that particular function. So that's an example of how, for example, you might do the approach that you were talking about last time, to where you're basically trying to control several things at once. And so,
I thought the example of extract like this extracted up instead of a servo unit delay.
right. That's kind of the idea behind it. And so you can see the module here is very simple. We we're just toggling the blinking LED. So this is what the filled in code would basically look like. So when you are looking at something like this blink on with the get blinked rate, for example, all you do is you basically fill in the function. If you're returning a value, you just return that value. You don't have to worry about trying to translate it into something else. All of that's essentially handled for you by the code generation. And so basically it encapsulates everything into the class and gives you a nice starting point for being able to simplify the module. The other advantage that this has is, let's say that you have a module, let's say you have a blink module, or let's say you have a motor drive module, for example, and you've developed a robot and you have that robot and you've developed some source code in your main PC that basically is talking to that module. But now you decide, well, I need a module that basically, I want to increase the size of the motors and I need a different motor driver. Well, you can basically create a new module that has the same interface, basically give it the larger drivers, and now it's as simple as swapping out a couple serial connections and a couple power connections, and you can drive it from that same higher level interface. And so that's kind of the notion of the reusability of this. Another example would be in a classroom example where maybe you have a class robot that you've built up that basically does various functions. So for example, you've got the drivetrain on it, you have the thing on it. As a class project, you could have each class member or a team of class members redesign the drive module. And they could basically design the drive module, do the soldering on the boards, they could do all of that. And then they could actually plug it into the existing robot and use it as a test to see how it works. So that's an example of using this in kind of in a class setting. It also makes it a little bit easier to share in like a team module. For example, say we're doing Robbie. I could work on the neck, and I could create a module for that neck, and then we could basically daisy chain those modules together, and they all would be based off the same core system, all share the common interfaces, and so it would allow us to essentially work on those pieces independently, but still come together and kind of design it as an overall whole, then divide up the project into pieces and work on those pieces. So that's kind of the idea behind this. And so the main goal is to essentially provide a system that basically helps you generate the code and generate these modules, and then makes these modules easy to share. So that later on, if I'm a developer and let's say I'm really good at a drive mechanism and I've developed a really nice drive module, I could actually produce that drive module and actually hand it off to somebody, and they could basically plug it into their PC and control it. I can generate the driver, that driver, and everything is all generated automatically for it. So me as a developer developing that module, I don't have to worry about developing that protocol for it. I just define the interface, and then I basically fill it in, and all of that's given to me. And so now I can share that module more easily. And if I'm someone who doesn't know about electronics or anything like that, I can still plug this in, and I can still drive it over that interface. And so instead of working with the actual individual electronics, I can work with somebody else's modules. So for example, an example of this would be, for example, the club. If we wanted to build a starter robot project, we could create a series of modules that people could buy from the club, or get from the club, or get the designs from the club, and then they could build a club robot that might compete in a basic event or something like that. They could still work on driving the high-level control. They could still work on the more of the mechanical design, or that could be provided as well. But you can eliminate the ability to have to go down and dig into the details of the electronics by essentially packaging some of them up into some modules that we could support. So that's kind of the overall goal of this, is to essentially, you can develop a set of modules, and then those modules themselves become something that's actually usable for helping to create robots, or helping people to create robots, or learn about creating them. So that's kind of the goal of the system. So any questions or anything, or comments, or what's that? So right now, I'm developing it for the Pico. In the future, I'm not planning on doing Arduino, but I am planning on doing an implementation using the ESP32, because the ESP32 is another very common, very powerful microcontroller to use. The nice thing about the Pico and the ESP32, though, is that you can use those microcontrollers in place of the Arduino, but you can still use the Arduino IDE if you want to for your main IDE for the coding and all of that. Also, right now, the code generation for this is generated for MicroPython. I did that primarily because it's very quick for kind of debugging and kind of working out the system and all of that. But the interface itself, the protocol, also has a C implementation. So with a few tweaks and a little bit of time, I can, instead of generating a project in MicroPython, I can generate a similar C++ program for those that would rather program in C++. It would still generate the same framework, still use the same backend protocol, still use the same communication scheme, but you would be able to basically program your module in C++. And you would gain quite a bit of speed when you actually use the C++ implementation as well, as the Python just by its nature is a little bit slower, especially on a microcontroller. So those are some of the future directions for for being able to take this. One of the other things you get that I haven't shown in here is, I mentioned kind of in the intro before that one of the things that we typically do when we're building these things is we throw in a whole bunch of debug prints, and to basically, as we're trying to debug and work with our modules. This protocol system also has a logging system in it. So it has a multi-level logging system in it, so that you could basically send log messages back to your host PC. I'm also planning on implementing another key feature that's actually that everybody uses, especially in robotics and when you're debugging, and that's to actually have a plotting system in the interface as well. So that's another thing that I'm working on at the moment. And what the plotting system will do is, unlike the Arduino, to where you basically just serialize out a stream of data, you'll be actually able to define a plot in the interface. And by defining a plot, is you'll be able to define essentially what the value is that you're plotting. You'll be able to name it. You'll be able to basically specify its type, and you'll be able to basically have multiple data streams. And then you'll be able, from within the code itself, to basically just call plot. You'll have a plot method that'll be generated, that you basically just pass the data to as arguments, and it'll send the plot back to the main PC, and it'll plot it. And what that will allow you to do, unlike the serial stream, is, since it's actually integrated into the protocol itself, is you'll be able to turn that plotting on and off. You'll be able to actually create multiple plots, so you could actually plot different things. So it's still going to go over the serial port going back, but the idea, but it's isolated, it's packetized. So like with the Arduino, when you're using the serial plotting, it takes over your serial and you can't use it for anything else. In the Arduino, when you use your serial for debug prints, that takes over the serial port and you can't use it for anything else. This protocol actually supports handling the logging over the interface, and it will handle the plotting over the interface. The other thing it handles that I'm not showing here is it also handles configuration. And what I mean by configuration is it's the persistent storage. So for example, if I have my motor driver over here, I might have I've got a PID loop in here that basically controls that's set for the motor that I'm using for actually setting the RPM. I can actually modify the PID parameters and have it save the PID parameters to non-volatile memory, to the permanent memory on the Pico, so that it can recall those on boot up. So right now the blink module isn't using that. So every time I restart the blink module, it resets to its default blink rate. But I could store the blink rate in a configuration variable, and it would actually store it on there so that when you restarted it, it would maintain that blink rate, for example. So the protocol actually will handle basically setting up that configuration and storing all of that for you, and also retrieving it into your class so that you can actually use it when you're writing your class to create your module. So there's a lot of very powerful features that are actually in the protocol behind it that will allow you to do certain things.
So you talked about 3 styles of communications at the outset. There was the commands, which return a value, and I see that in like get delay as an example. There was the messages, which are like a publish sort of function. I see that in the turn the LED on. And then the other one was the events, and you said that modules can emit events that can be received by other modules. So that implies a sort of a multi-master peer-to-peer kind of communication. Can you talk more about the capabilities? Because it sounds like you would need to deal with maybe not need to deal with arbitration, because if you're handling characters one at a time, you could buffer them up while you send out an
Exactly.
event. Is
Yeah.
is that implemented or
That's all implemented. Yes.
wow? So you
So
can do like peer-to-peer,
you can do peer-to-peer with
And-
the system.
and it sounded like peer-to-peer would be messages, not commands.
Correct.
Okay.
Peer-to-peer is messaging. So basically there's the interface is basically made up of several sections, as I've got up here now. So one is the required assignment. So those are things that are required for identifying the module. So it's like the module name, the version number.
If you could share your screen so
Oh,
people,
the screen's not sharing again? Sorry about that. Is it sharing again?
Yep, thank you.
Okay, so required assignments are essentially, I don't know if, well, it probably won't show it. So they were things like the version number and things like that. There's commands. Commands are essentially meant to be initiated from the main controller. So, and they're a command response.
It's a remote procedure call.
It's basically a remote procedure call. So you're sending down the command, and then it's returning a value. A method is essentially from the main command, gets sent down the chain, and method goes down the chain but has no response back.
So it sends a message.
Right. Events are kind of like messages, but events are from the module back up to the host or to other modules. So you can think of it, if you have 3 modules in the chain, for example, if the module in the middle sends an event, the event will go basically propagate out both directions down the chain so that anybody that's listening for the event can actually handle the event. Event handlers are essentially the methods that actually handle events. So the way these get implemented in the class that gets generated is for events, you get a method call that basically triggers the event. So you can give it arguments for the data that you want to send for the event, and then you can basically fire the event just by calling that method, and it will fire the event. An event handler is essentially a function that'll automatically get called by the system whenever the event occurs. And so in your class, you'll get a function that basically has the signature for the event. And whenever the event is detected in the communication layer, it will actually call that method to allow you to handle the event. So all of that plumbing and all of that is actually taken care for and is automatically generated from the interface.
Let me like to give you an example, and you can tell me
Okay.
how.
Okay.
The motors, your little robots turn on. It hits a wall. Wheels stall. That's an event.
Mm-hmm.
And to essentially shut off that motor or an escape mechanism or some of our motors, you've got about 2 seconds in the stall and then that's it.
Yeah.
So you got to figure out.
So in this case,
Well, maybe you say for protection, you might say
the
speed is dropped to 1/10 of what it's supposed to be.
yeah, the way that I would implement that in this system is I would have the module itself would basically detect the stall event. So the module would be able to immediately handle the stall event. So it can say, I stalled, I'm stopping. So it would actually stop the motor so it could respond basically as fast as the microcontroller could respond to it. It would then fire off an event that says, I stalled, which would then go down the chain and notify anybody else down the chain that a stall event has occurred. And anybody who was listening for that stall event could then handle that stall event. But the actual motor stall event would be handled by the motor controller, so you wouldn't have to worry about any delay to get up to some master control to stop the motor, for example. You could actually stop the motor and the motor control driver.
Then handler would be essentially your escape procedure, whatever it is, go back.
Right.
I'm just throwing out,
Mhm.
you know.
Yeah, it could be go backwards. It could be.
After it's already stopped, so you have to restart it to go backwards.
Yeah, that's the way I would do it personally. So you could do it the other way to where you had all of your handling up at the top level, but then you'd have to wait for the event to propagate. Then you'd have to propagate a command back down, and so there would be more delay that way. And in a case like a motor stall, that would be one where I would handle that in the module level, and then just have the module as part of its interface have the event that it could say that I had a stall.
And yeah, and so presumably you can have multiple, if you will, subscribers, to use the publish subscribe terminology, multiple subscribers to events. So you could have like downstream motors subscribe to that, to have an event handler and shut off their motors, as well as the master controller have an event handler that
Right.
shuts things down and takes a higher level action.
Yeah. So the protocol is a packet-based protocol. So it basically is sending packets of information. So a packet might be a command, a packet might be an error, it might be a plot command, a logging, and so those are automatically managed over the serial interface. Like you said, there's all kinds of code in the bowels of things that manage collisions and all of that to keep things from colliding and keep things flowing smoothly. Also to keep it from overloading, so that one device can't completely overload and block everybody else from sending down the chain. So there's mechanisms to stop that as well.
I got it.
Want me to wait for you to get back since I'm answering your question?
Hi. What's up? Yeah, can you hear me?
I had a basic question, and that is,
Mhm.
you have several modules linked together, and one of the modules
Yeah.
is the master.
Yes, one of the modules can be the master.
Is it not a pi?
Yeah.
It doesn't have to be a
How
Pi.
about
It could be
how about
it could
I
be
get home by
it could be
2,
another microcontroller. Yeah.
or 2 or 3. Actually, I
So
prefer 3,
um,
but
there's
yeah,
other advanced
I'll definitely be home
features
by
that
3.
that the protocol supports as well.
That'd be great.
That will
Thanks.
kind of help
Bye.
deal with that in the future as well. I just need to, like I said, this protocol is something I've been developing for a while. The tool set I've been building up to make it a little bit more accessible is something that I've been actively working on, or at least as actively working on as I've been working on it.
You had one module that's the master controller, you can still plug in a PC over the USB.
Yep.
And monitor.
Mm-hmm.
So can you run the master controller on another Pico?
Yes, in theory
Okay.
you can. And the reason being is all you're doing is sending commands, and every module by definition knows how to send commands and process commands, otherwise it wouldn't work.
Yeah. Yeah.
And so it'd be just as easy to have a master one that basically could basically implement you would generate a driver for the microcontroller, which would be a MicroPython class that you would basically install on your master program, and then you would use that to basically send and talk to the protocol. So what the driver is, in essence, what the driver is the driver takes a simple Python method call from a class and takes care of all of the argument translation to translate that over to the packet format that's then sent across the wire. And so that's the driver that would be generated for that you would use on your master to basically drive and control everything.
So why did you choose to have a master-slave concept in it when it, as well as, I mean, I understand why you want events, but events can be master-slave just by
themselves,
conceptually, right? By saying, okay, the thing that emits.
because oftentimes, especially when you're trying to teach people and younger people, the mechanisms, a lot of people have trouble understanding event mechanisms and how event mechanisms work. And it's when people are learning programming,
Yeah.
they tend to learn more of a serial approach to programming.
Yeah.
And so the idea is to basically support both, because you don't always need the full-fledged events, and events actually carry some overhead. And so being able to just basically have a simple serial communication like what most people are used to, and having the option for both gives you some flexibility.
Then let me flip it around. Why do you have the limitation that there can only be one master? Why couldn't each module have command and messaging capability?
It could.
I'm not sure.
You can do that, and in essence, that's kind of what the event system lets you do. The event system lets you basically create that system, but those systems tend to be a lot harder to understand and a lot harder to control and a lot harder to tease apart when you're trying to debug them and work things out. That's one of the things that actually makes ROS difficult, is its event-based system. Because of the fact you've got all of these things that are all communicating with each other in this big, massive network.
Yeah.
It's easy to develop a system that doesn't have a good flow.
Okay, maybe I didn't ask my question quite right. It seemed like the command notion has an implicit master being the thing that receives the response.
Right.
And so my question is, could potentially two modules issue commands?
Yes, potentially two modules could
And get
issue
a response
commands
that comes back to them.
and we get a response that would go back to them. But again, that's going to confuse the system if you have two things that are fighting for control over the one thing. There are times when you want to do it, but in general, you want to try to avoid it.
Yeah, thanks. I'm just trying to understand.
Mm-hmm.
So you could have one master controlling 6 threads.
Mm-hmm.
And you could have another master controlling multiple boyets.
Yes.
So otherwise, you started at the beginning. You said something. I don't know what the word.
You can have multiple chains. You can have multiple chains.
So each chain has to have a master.
So yeah, so you can think of each chain as having a master. So that would be, in my mind, a better way to kind of design what you're talking about. Would be to essentially you would break up your modules into different chains for doing different functions.
So somewhere there's got to be one.
Yeah, somewhere you want something that rules it all.
Yeah.
So
And it sounds like it must use 2 serial ports on the Pico. Is that correct?
it does use 2 serial ports. It uses one for the incoming and one for the outgoing. So it does use it uses the 2 UARTs of the Pico, but it leaves everything else available. So all of the I2C are available, the SPI, the PIO, all of that is still all available. And with the PIO, the reason why I chose UART for a couple of reasons, but one of the big ones in the Pico is that one of the easiest things to create with the PIO is a UART. And so if you actually need a UART, you can create one using the PIO rather easily. In fact, from Raspberry Pi, you can get examples of exactly how to do that. And so if you still need the serial port, you can create one on the Pico using the PIO. Right. My other reason for using the serial is, as opposed to other protocols, is it gave me the freedom to do the dynamic addressing and stuff like that a little bit easier, and also to control the daisy chaining. So the overall protocol has the notion of a command. The way the command is sent is the command is addressed. So you give it an address, and it basically travels down module to module, and it's basically chaining through, like I said, one character at a time down the chain, and everybody's basically decoding it. If they see that it's for them, then they process it. You also have the notion of tokens, and what tokens are is when you send a token down the chain, tokens are handled differently. A token is consumed fully by the first device, and then it will decide if it needs that token or not. If it doesn't need that token, it will pass it on to it'll pass it down the chain. And so it allows you essentially an interrupted scheme of doing communication. And right now, that's only used for the addressing. So what I do is I send out, well, I guess first I should say, so each one is dynamically addressed. You can also group them. So you can have modules. You can group them together. So for example, on these two modules that might be blinking modules, I would, in theory, be able to group these together, and then I could call them at once, and I could set their blink rate at one time. So I could set the blink rate, and it would set it on both modules because I could set it to the group. So I can define groups. There's also broadcast messages that basically everybody can consume. So for example, the way the addressing works is when everybody boots up, they boot up with an address of -1, and they wait for a ping. And so the main program, in this case that discovery program, sends out a ping, and that ping goes down, and then that ping is sent to everybody. It's sent to address 0, which is basically a broadcast to everybody. So everybody pings back. As I get a ping back, the program receives the ping and says, okay, I got a ping from someone who's a -1. I don't know about him yet. So he basically says, okay, I'm going to send out an address token to the guy that gave me address -1. So the first guy on the bus that has a -1 address will receive that address token, assign his address, and then he's now addressed. The next one will send back, and he'll be a -1 now, and so I'll get another -1 at the master. The master will say, okay, I need to address him down the chain. So it'll send another address token. The first one's already got his address, so he ignores the token and sends it to the next one. The next one grabs the token and grabs the address. So
just real quick before we break for pizza, what documentation exists for this?
What's that?
What documentation exists? Because this is a sophisticated system. It really is. And
There's a lot of sophistication to it, and there's and I need to create some documentation, and that's some of the stuff that I'm working on.
okay.
And that's why this isn't publicly released to a GitHub yet.
Cool.
But I wanted to kind of introduce the system, and like I said, the other thing is I wanted to see if anyone might be willing to be a guinea pig and maybe try designing some modules when I'm ready in about a month or so, would be willing to work with me and trying to refine the system and get it ready for release. So,
Think about that.
so if anyone's interested in that, please let me know.
Very cool.
So that's kind of the idea behind the system. The idea is to kind of generate a lot of that stuff that we normally spend a lot of time doing, and try to automatically generate that on the fly, so that you can concentrate on creating the module. Or if you don't want to concentrate on that, you might be able to, let's say I need a drive module for my thing, but I don't want to do the electronics. I could say I want this interface for it, and I could ask someone to help me build that module, for example.
Cool. Well, thanks, Mark. That was a great talk. And I'm sure if anyone has questions,
Anyone else
Good
has any
luck.
questions they can ask?
otherwise,
What's that? Yes, you can run it on a Raspberry Pi, but it's designed around the Pico microcontroller. I actually intended to for the overall system to basically use the Raspberry Pi as kind of the master controller. So it would basically initiate the chain. The other thing that I didn't go into yet is kind of what's next and what's to be expanded. But we can maybe cover that after lunch. So
over to you.
I had one last slide that we didn't cover, and that's my what's next slide. So there's still some things that they're left to be done to kind of get this thing ready for use. I'm working on a couple of rewrites on the two main control programs, the one for generating the code, and also the one for displaying the thing. Currently, I wrote them using WX Python for the GUI interface. And WX Python and getting it to work sometimes with the Raspberry Pi or whatnot can be a little bit difficult. So I'm trying to streamline that to where it doesn't rely on those dependencies. So I'm planning on just using on converting those over to just use Tkinter so that they don't require any additional libraries, which will make them more portable. I also want to create some command line tools because, especially in robotics, a lot of times the main computers that we use for driving everything don't run a graphical user interface. So being able to do everything from the command line is also important. So I'm planning on using I'm planning on still having some graphical elements, but I'm planning on using textual, if any of you are familiar with that, for basically doing command line GUI. But it can be run completely off the command line. Then there's a few features for the discovery tool that I want to do. So one is adding in the support for the configuration parameters I talked about. So you'll be able to essentially, as part of the interface, you'll be able to pop up a table of the configuration parameters, and so that you can enter in those configuration parameters. It'll then be stored to the board, and that will give the board some persistent storage. Support for the plotting is one of the other next ones. Like I said, I want to have support to basically support what most people use the serial terminal for, and make it a little bit more useful. And that's to basically put in a plotting system to where you'll be able to actually define multiple plots for the module, so that you could turn on and off plots as you need them, so that you can, for example, so that you can leave the plotting in there in the module itself and be able to turn it on and off at will without it cluttering up the traffic on the interface, on the protocol itself. Likewise with the logging, I have the support in there for the logging, but I don't have the control for it in that program yet for being able to set the various logging levels. So currently you can set a logging level so you can control the level of logging that you're actually getting out of the system. Other things, I'm trying to read my screen is too small and my eyes are too bad at the moment. Support for multiple return values. Currently, commands can only return a single value because they're kind of limited by a Python function. So the protocol supports mixed return values and everything. So I want to add in that support to where you can essentially define a structure and return a structure so that you can return more complex return values from your commands. And the last one was the more control over logging. So that's kind of what some of the things that I want to rework in the tools before I release them, and some of the things I'm working on. Like I mentioned before, I'm also working on creating a dev board that to make creating the modules a little bit easier, to give you kind of a starting point. So the dev board actually consists of it's a main board that has a Pico on it, and then it has the connections for basically doing the chaining, for being able to chain the modules together. And then similar to an Arduino, it's kind of based off of a hat idea. So you basically have a prototyping hat. I have two versions of the hat. I'm using Easy EDA for creating these. I found for me that it's the most straightforward tool to use, and actually the one that whenever I go to find components, it usually has them, unlike most other ones that I look at. Mainly because of the fact that PCB makes so many PC boards, and they're the ones that maintain it. So they actually do a good job of adding all of their inventory and whatnot to it. So, and they carry a large inventory because they create so many boards for so many different people. So I find that their tool actually has most of the tools in there. So anyway, I'm not very good at PCBs yet. So I think this is my third one. But so the idea behind the board is it provides some other features as well, but for the module. One is that, like I said, it's designed to run off of a power feed that's 6 to 30 volts. So any power supply 6 to 30 volts, you can actually plug up to it and it'll run off of that. So if you're building a robot, for example, you could put in a 2S or a 3S battery would be is like a typical battery for a robot.
Those are 25.6, right?
26.7 is, I think, is nominal.
Yeah.
30 good choice.
Yeah, 30 is good.
Yeah,
24.
no, I deliberately went a little bit above 24, but because I meant for 24 to be kind of the again, where this kind of grew out of is it grew out of me building industrial probers and things like that. So we deal a lot with 24-volt power supplies. And so being able to create the modules and have that available. Or another common one is 12-volt, because a lot of motors and whatnot like to run off a 12-volt. So the idea is that so you can feed it with 6 to 30, and then on the hat you actually get outputs for the high power, which is the direct battery. So you can wire that up directly to your motor controllers and that. And then there's also a 3 amp switching 5-volt power supply that drives off of it. So it also gives you a 3 amp 5 volt supply, which is good for things like servos and things like that. So that if you're building around this board, you don't have to worry. It already manages your power. So frequently when you're building up a robot or whatnot, you have to add in your power regulators and all of that for all of that. This helps give you some of that off of the bat, so you don't have to add a separate one.
Pico coming off the 5 volts.
The Pico's coming off the 5 volts.
But the daisy chain
And
also support it, sends 5 volts to everything.
right,
Just for a simple use case.
right. So in the simple case where you don't need the high power, you can actually get it through the daisy chain. The problem is the daisy chain, depending on what your initial feed source is, may not be able to support X number of modules, because you do get a power drop as you go across, obviously. But the idea is that if you had a simple sensor module, for example, that only required 5 volts, you wouldn't have to hook it up to the high power line. You could power it off of the daisy chain connection.
What about availability of 3.3 volts?
The 3.3 volt is available, but it's coming off the regulator from the Pico. I
Okay.
didn't add a separate 3.3.
Okay.
It's one of the things that if people want that could be added in the future, but I was planning on just using the 3.3 off the Pico, because normally it's enough for driving what you would want to do in a typical
Right.
module.
Right.
Because you
3.3 volt
normally,
sensor or
yeah,
whatever.
because you typically don't need much power for that. So
Could be one thing that would be cool to have, especially if you system with 5 and 3, is that your I2C, if you're using that.
yeah, to have
to
level shifters. Hmm. Yeah.
It's like 3.3 on the 3.3 side.
Right.
Yeah.
Because these days, just about everything is 3.3 and 5, because like,
TF Mini Pro, which is a very nice TOF sensor.
Hmm.
Serial port is 3.3.
Right.
Power supply
Is 5.
is 5.
Yeah.
Right. That's actually the primary reason why I put the 5 volt regulator on here, is because typically most of the modules their communication is 3.3, because all of the modern microcontrollers are all 3.3, but they oftentimes have a power requirement for being powered off of 5. And so by having the power regulator on here, you basically have that 5 volt that you can tap for that power. And the grounding is already taken care of and everything, so that they're on the common ground. And so you can actually use that 5 volt power to power them, but still talk to them with the 3.3 directly from the microcontroller. But that's one of the things that I found whenever, like for example, most of the modules in our prober system were 12 volt, because we were switching 12 volt relays to switch things on and off, but we were controlling them with the 3.3 signal on a thing. So we had to have the 12 volt power to it. We had to have the 3.3. And then of course, most of the microcontrollers don't power directly by a 3.3. They power by a 5. So now you have to have a 5 volt on there. So I wanted the board to have, much like the older Paulu A squared boards, and even the Arduino, had the ability to essentially drive them from a higher voltage, so that you could drive everything. So I wanted to make sure that this board had that as well. So that was kind of the design impetus behind this. Is when I go to work on a project, I don't want to have to worry about, okay, now I've got to dig out a 5 volt regulator. Now I have to dig out something to handle a 12 volt battery or a 12 volt DC supply. And then I need to wire all those together. And that's all stuff I have to do before I can even start to control the motor driver from the microcontroller. So the idea behind this is to simplify that and essentially have all of that already here, so that when you go, you can plug in your module, you can hook up your 5-volt. If you need the higher voltage from there, you could hook up the higher voltage directly. And so you can start wiring everything up directly. You don't have to worry about mixing and matching, trying to get all these modules. Everything's on the board. And then the idea behind having the pre-made prototype boards is one, I can label them so that they're labeled on the sides for what all the pin mappings are, so that you know exactly where to wire them up. This is something that if you were building this for someone, you could easily build up this module and give them this module, and this would be cheap to build up, and then they could buy the baseboard and plug the firmware into it.
That's one of those.
So basically, that has all of the extra pins that are on the Pico are mapped to that board. And so they're labeled top and bottom so that you can wire it from the top, or you can wire it from the bottom and you don't have to worry about flipping it over.
Nice to have a connector for chain.
Yeah.
Going to pass some of the other boards down too.
Yeah. So that's the base board. These are just some of this was my first version, so it doesn't have the 5-volt regulator or anything, but was just a proof of concept.
These boards are not soldered on, they're just like, right? Or are they soldered on?
Yeah, they're soldered on.
Oh, yeah.
So that, one of the white daisy chain connectors is your current version?
Yeah.
Yeah. 'Cause
I went with a bigger cable to handle the larger power requirements.
I've had
Oh.
troubles with those smaller. They're
Wow.
unreliable.
Yeah. My original thinking on it back when I first designed it was that those cables are readily available from Adafruit, and Adafruit uses them for all of their connections. So I figured I could get the cables for cheap, and everybody might have them already around for dealing with Adafruit with Adafruit modules. So that was my original thinking on that. But then when I started adding on the 5-volt power and wanting to drive it at higher voltage and whatnot, I decided to go to a little bit bigger connector and bigger cable.
Easier
Right.
with that. Yeah.
Right.
Custom cables.
So that's kind of what the so that's the idea, is that you'll be able to get that board. The other thing I plan on doing is I'll probably have to share this again because I'm going to shut this down and it's going to scramble again. I also plan on this being kind of an educational or teaching thing as well. So I also plan on making available this guy.
It's not shared.
I know, I'll share it here in a moment. Let me go back to sharing.
You got both sides.
All right, hopefully it's sharing now.
It's sharing.
So I plan on making available this Easy EDA project, which is essentially, it's a project that basically has the blank proto board. And so if you're wanting to experiment and learn PCB design, for example, you could use this as a starting point to create a PCB that you could plug the modules in directly and solder them. And so it's got the, so it basically has a, I hate the way this thing acts underneath the, So it basically has a project already set up with the pins and everything. So you've got a starting schematic and a starting PCB layout that basically for the hat. And so if you're trying to learn PCB design, you could use this to as a jump start to create a PCB. So you could once.
I do have a suggestion. You should include over to one of your goals.
It is.
It's in a very level there.
Huh?
I mean, otherwise, where you are now, you have your sockets.
Yeah. And if you look, the holes that are immediately adjacent to the sockets
Should be.
are tied to the sockets. If you look at the PCB traces, they're tied. You may not be able to see it, but they're tied. The signal wires aren't wide, but the power wires are actually wide. I can show you here on the.
I don't think it's. I would see the PCB.
Yeah, hang on here a second. Easy EDA, it's easier to start it from scratch when you're loading a new project. It's more reliable that way. See if I think it shows up a little bit better in the. So you can see that they're all connected over to that one trace. The grounds are bound to the overall ground plane, and then it's connected over. And if you look at the all of the power traces are a thicker, heavier trace. So if you come over and look at the high power traces, they're a thicker wide trace on the thing for the power as well too. So they're all connected over. And then like I said, all the grounds are connected to the actual ground plane of the proto hat. So you can basically reach ground from more or less anywhere. So that's the idea for the hardware. And again, when you're learning and whatnot, it's to try and simplify that, to kind of bring everything down to normal. So you'll probably start with the breadboard first, but.
Did you have them stuff this one?
Huh?
Did you stuff it?
I stuffed it. You want to know the secret?
Oh yeah, tell us the secret.
Hot plate. No, yeah, I
thought
use.
You were gonna tell me 42.
No, I use I use a hot plate. So I basically have a JLC PCB or whoever. That's who I had to do these. Well, actually, these are from Osh Park. The initial ones are from Osh Park. But I had them make me a template, a solder mask template. And so I just basically lay out the template, smear on the solder paste, and place all the components by hand, which is tricky with some of the smaller ones, but doable. And then set it on a hot plate and let it solder. It works really, really well.
So Pat asked if it works with Pico 2.
Yes. So I didn't mention, and I guess I will mention now. So I actually, in order to keep the footprint lower for the Pico project, I actually compile the micro Python myself. So I actually generate a micro Python where I actually embed some of my helper classes and whatnot into it. And so it basically helps to lower the distraction level for the Pico version. It also gives a little bit of a speed increase because those libraries get compiled into the the Pico, into the MicroPython binary itself. It's actually, Raspberry Pi makes that really easy to do. Maybe one of these other times we can discuss that, or I can show how that's done. But yeah, so you can actually you can embed your own MicroPython into the MicroPython interpreter directly, and so it does some pre-compiling steps on it and whatnot. So it actually will run faster, and that's what so that's how I manage a lot of the stuff in the background. So most of the main protocol class and some of the helper classes that I use are actually compiled into the MicroPython binary itself.
And you were going
And so it's actually that code will all run on the Pico, the original Pico, the Pico 2, the Pico 2W, and the Pico W as well. The communication protocol is kind of like I said, it's just a simple serial stream of data. And so right now, the Pico will automatically detect and switch between whichever talks first. So if the USB talks first, it'll hook that up as the primary input. If the serial port talks first, it'll hook that up as the primary import. And so it'll auto detect how you have it connected. In the future, what I want to do is have support in there for the Pico 2 and Pico W, so that one of the auto supports will be if you connect to it over Wi-Fi or Bluetooth. And so it'll still be a serial protocol over it, but you'll be able to do the connection over Wi-Fi or Bluetooth. I haven't decided which one I want to tackle first yet. Wi-Fi is the simplest in my mind, but it's also the one that has it's got a little bit trickier setup. And but I'm planning on implementing a wireless protocol, so that you can actually connect to it wirelessly.
Would it like be using your computer?
Yep.
Protocol as the debug?
Yep.
And
So right now, if you remember when I popped up that discovery program that showed the interface, I dropped down and I selected a serial connection. It allowed me to pick the serial port. It would just have another option in there to connect wirelessly, at which point it would basically allow you to enter in the IP address or whatever, so that you can connect to it wirelessly. And then it will, and so that way you can, once you have your robot set up, you could have the first module be a wireless module that basically receives all of your wireless communication, so that you don't have to be wired to it, tethered to it. Haven't gotten there quite yet, but that's on the roadmap. And part of the reasons for doing this today was to give myself a kick in the butt, so that if I get people that are interested in it, it'll give me motivation to finish it. Any other questions before we wrap up?
you were saying you wanted people to help. What does that mean?
So basically what I want guinea pigs. So I'll provide you a dev board and let you create a module, and let you go through the process of creating a module and trying to use it. And maybe building multiple modules. So someone other than me is actually trying this stuff to help me find the little subtle flaws that I missed. I'm a software developer. Of course, I'm going to miss all the subtle stuff. If I was a hardware stuff, I'd screw up the hardware. But since I'm software, I screw up all the software. So that's what I'm looking for, is a couple people that I can kind of work with one-on-one to to try out the system, try and develop something, and let me know the likes and dislikes of it, and if there's any changes that need to be made, and help me basically get it ready for a more general release.
And how can people contact you to?
The easiest way is through my email, and my email is mark@dombrowski.com. So that's mark@dombrowski.com. So first name at last name.com. Or you can also ping on Discord, and even though I haven't been active on Discord, I do follow it in the background. So if I notice messages, I can look on Discord as well, or through the DR. I'm also on the mailing list. So
Through the DPIG email or something
Right.
like that. Cool. All right. Last questions, last call. Going once, going twice. All right. Thank you, Mike.